Hello everyone, welcome to my video explanation about some features of electric fields and electric field lines. To start, let's talk about what an electric field is. An electric field is defined as a region around a charged particle or object within which a force would be exerted on other charged particles or objects. That might sound kind of confusing at first, but I think these equations help explain that a little bit. So let's start off with them. These are just some equations you'll need to understand electric fields, and they're going to be important to your homework, so let's get a hold of what these values mean. For the first equation, we have the electric field E here. You can see E, the electric field, which is defined as F, the electrostatic force, over Q prime, which is, in this case, the test charge. So a test charge means that it's a charge that's small enough to not significantly affect the electric field. So just keep that in mind. The second equation here, we have E, again, the electric field, is equal to KQ. So K is this constant over here, 8.99 times 10 to the 9th. Q is the charge, and that was all over R squared, and R is the distance from the charge Q to the test charge. So just keep in mind those equations are important. Now let's look at field lines and some of their characteristics. At first glance, these lines might seem hard to interpret, but if we understand a few simple rules, they can tell us a lot about the electric field. So, to help us better understand what's going on, let's outline some rules with electric field lines. Firstly, field lines never cross. This is pretty obvious to see in the illustrations over here. You can see that the field lines are never crossing anywhere here. Secondly, we can understand that more dense field lines correlate to a stronger electric field. The more lines that there are in a defined space, the stronger the field. So let's walk through some examples here at the left to make sure that this makes sense. So obviously you see in A and B here that A, the lines are further apart and they're closer together here in B, so that's a stronger field. Kind of a similar thing, but with a point charge here. You can see that this is a stronger field that has more lines coming out of it. This is a weaker field with the lines not as close together. Now this one might be a little more complicated to understand, but F is experiencing a weaker field than E, because to F, if we were to draw like a little circle around it and to draw the same size little circle around E, the lines are closer together in E than they are to F. Okay. So next, we can see that field lines start on a positive charge and end either on a negative charge or go to infinity. This means that arrows will point away from a positive point charge. In fact, we can think of arrows as pointing in the direction that a positive charge would move. This makes sense because like charges repel, so a positive charge would fly away from a positive point charge. On that same train of thought, an electron would move against the arrows of the field lines towards the positive charge. This also makes sense because opposite charges attract. Lastly, we can see in this illustration that negative point charges have electric field lines that point inward. Alrighty, let's talk about conductors. The first thing to understand about conductors and electric fields is that electric fields do not exist within a conductor, meaning that electric field lines will not be present inside a conductor. You can see that in our example here, with this spherical conductor that does not have field lines within it. The field lines appear to come in one side and go out the other without passing through. We can see that the field lines will come in or go out of a conductor perpendicular to its surface. You can see that in this example, in all of these lines, that it comes in perpendicular, or in this example, perpendicular, and comes out perpendicular as well. Next, we see polarization of the conductor when it is put in an electric field. This means that the negative charges will come to one end, and the positive charges will collect at the other side, which you can see here. So all the negative charges are along this edge of the conductor, and all of the positive charges have gone to the other side. Let's talk about how charges are distributed on a conductor. On a sphere, charges are uniform, as you might expect. What is important to understand, however, is that on an oddly shaped conductor like this one, this avocado-looking thing, Charges will be concentrated at the pointiest spots. Hence we see concentrated charges at the tip of the avocado. You can see that they're a little bit more sparsely distributed, but up here they're closer together. And that's a general theme with conductors, that the pointier ends will have more concentrated charges. Let's talk about vectors now. Electric fields can be represented by vectors. This is especially useful when you're solving problems that involve multiple charges that create multiple electric fields. Vectors, as you know, can be added together using a bit of trigonometry. For example, you could calculate the electric field that this green star is experiencing due to the 2 point charges here and here. You would do this using the equations that I showed you at the beginning of the video and then adding the vectors. Okay, that's it for my video about electric fields and electric field lines. Let's have a quick review of the important principles that we learned today. We learned that every charge creates an electric field. Using this equation, we can solve for that. Field lines point from positive to negative, and they never cross. The closer together the field lines are, the stronger the field. Conductors do not have field lines inside them, and field lines end perpendicular to the surface of a conductor. Charges distribute evenly on the surface of a spherical conductor and collect in pointy ends of conductors that aren't spherical. Electric fields are represented by vectors, which you can add together for multiple charges. Thank you.